last week, and we have seen basics of algorithm analysis, at least the several first slides. So we talked about algorithm efficiency, and we went first through how we might quantify algorithm efficiency, and we said that testing the algorithm for few input vectors is not really what we want to do, and we said that we are going to do it more theoretically by finding out what is the number of runtime steps in terms of the size of the input. So we reached some nice diagrams where we have seen two algorithms which implement the same functionality, but they have different growth functions. And we've seen two cases where one algorithm is initially better than the other. So we have seen that case here, where A2 is initially better than A1 in this range here, but then we said that eventually A1 is better than A2 here, A1 is better than A2 here, and so A1 is going to be better than A2. And we started developing this understanding of asymptotic complexity. Basically, an algorithm is better than another algorithm. We are only interested when the input size is very big, is towards infinity. So I think we have stopped here last time. Okay, if we go back to the examples that we have seen, I think the microphone is in one of the rooms is on or something, because I hear my voice back.
It's all right here.
Okay. So in these two algorithms here, when we talked about the different steps, we said that this is one step at runtime, and then we said that this is one step at runtime, and there are n steps here at runtime, and this is another one step at runtime. So when we did the analysis for these algorithms, we have assumed that all these steps are equivalent. Okay. For example, if we have some algorithm, okay, let's take some example. Okay. So let me give you an example of some function. So let's say we have some program P that takes some input n. Okay, and let's say we have some program P that takes some input n. Okay, and program P has got statements inside it. For example, x equals x plus 1, y equals a times b, and then we have a for loop which iterates over I from 1 to n, and it has z equals d over e, and for example, and something else, another assignment statement, x equals x plus 1, and then we finish the loop. Okay, so that's just an example, kind of random program to make the point. Every statement here that we see, this is an assignment, this is a multiplication, this is a division, this is another assignment, and also it has addition, and this one also has addition here. So these are different statements. If we execute them on a computer, they will take different execution times. Okay. For example, this assignment here is going to be executed using a simple adder. For multiplication, you will need a multiplication unit. For division, you will need some hardware unit that does division, or perhaps a software routine that does the division for you. So in other words, every one of these statements is not going to take the same execution time if we measure it on the hardware. However, for our analysis, we really don't care about this kind of differences in execution time. In our analysis, when the input is very large, the differences in execution time between the different statements in the algorithm is negligible. Okay, to make the point even clearer, let's say we have algorithm A1, which takes input n, and there is a for loop from 1 to n, and we have some statement, for example, x equals x times 2, and that's the end. Okay, and another algorithm A2, which basically also contains a loop, which also iterates over n times, and it has the statement x equals x plus 2. Okay, and then we try to plot the functions of, like we did last time when we found the constant growth function and the linear function. Okay, so if we try to plot the functions here, they're both going to be linear. Or let's not plot the function. Let's just think about the time that the algorithm is going to take. Let's say that the input is 1 million. Okay, let's say n is very large, and let's say very large is 1 million. Okay, so n is 1 million. Okay, let's say n is very large, and let's say very large is 1 million. Okay, so n is 1 million. Let's say that in order to execute the multiplication, we execute it in 3 nanoseconds, or 3 nanoseconds, and in order to execute, or 30 nanoseconds, in order to execute addition, it takes, let's say, 5 nanoseconds. Okay, so this 30 nanoseconds here is going to be repeated 1 million times. So that's going to be 30 times 10 to the 6, and that's going to be 5 times 10 to the 6. Now, if the input was 10 to the 9, that's going to be 30 times 10 to the 9, that's going to be 5 times 10 to the 9. Now, if you can see what's happening here is the size of the input is actually what is going to determine the number of steps. Okay, it's not really this 30, because if the size of the input here is, I mean, if we write this number down, okay, that's going to look something like that. This number, what is affecting this number actually is the 10 to the 6 more than the 30 here. Okay, the more the input, the larger the execution time. If we have more input, the effect, or if we have input of larger size, the effect of the execution times of the individual instructions is very low. Okay, so that's what I wanted to say by that slide. So this is what I wanted to say by this slide here. What I said is the different statements in a program, they will not always execute in the same manner. Okay, they will not have the same execution time. The statements will change. The execution time will change because of the implementation of the statements at the assembly level, because of the hardware features like caches, multi-level pipelines, multi-core processors, etc. However, in our analysis, we do not care for these differences in execution times between statements, because when n is very large, the differences in the execution times between statements is negligible. It does not affect the execution time of the algorithm as much as the size of the input does. Okay, so when we look at the execution time, when n is very large, the differences between the different statements is negligible, and this is called the random access machine model, in which basically we are saying we don't care about the differences between the execution time. So the results that we obtain in this course, theoretically, by not assuming a particular hardware architecture, will still apply in normal life situations. So if we apply in normal life situations, so if we run an algorithm, if we study an algorithm and we find that it is efficient because it's linear, it is going to be efficient on any hardware that you are going to choose. If we study an algorithm and we say it's not efficient because it's exponential, for example, it takes an exponential number of steps, then it will not be efficient no matter how fast the hardware is. And we will see an example at the end of this lecture. We are going to run a non-efficient algorithm on a supercomputer, which is the fastest computer in the world, and we will see that still it will take a long time to execute. So efficiency is not related to the hardware architecture. It's really related to the algorithm itself, how it's implemented, and how its growth function, or how its number of runtime steps change with the input size. Okay, so you can read about this in the book, the random access machine model, if you are more interested in that. So last time we have reached this conclusion that if we want to see how an algorithm behaves with respect to changes in the input, we plot the graph, which looks like this. We have the input size here, and we have the number of steps here. Okay, so the y-axis is number of steps, and the x-axis is the size of the input. And we plot a function that we are going to call the growth function. So this is called the growth function. It shows us how the number of steps in the algorithm grows with the growing input size. Okay, so we have number of steps in terms of input size, and the curve here that we draw is the growth function. Okay, so in the example that we have seen, this growth function is a line. Okay, and this growth function is a straight line as well. This grows linearly, and this one is constant. This is linear. This is and A1. This one here is constant. So this is a growth function, and this is also a growth function because they show the number of steps of the algorithm, the number of runtime steps in terms of the input size. This is an observation. When we write an algorithm, we said that an algorithm is a sequence of well-defined steps that solve a particular problem, and now we are talking about runtime steps. Okay, let's look at one of the examples again to see what is the difference between, these two things. So here, in figure 3, which is algorithm 2, the one at the bottom, this is an algorithm which okay, so this algorithm here, we can say that it has 3 main steps. It has the first step here is basically initializing a sum variable. The second step is to add the numbers 1 to n to this variable, and finally the last step is to return the sum that we find. So in terms of description, Okay, in terms of description, this algorithm has 3 steps: initialization, computing, and return. We can agree. You can say something else if you want, but it has to be logical. So these are the steps that describe the algorithm. This is what we meant by an algorithm is a well-defined a well-defined sequence of steps to solve a particular problem. Okay. Now, runtime steps are something else. Runtime steps, we will have sum equals 0, and then we will have sum equals sum plus 1, and then sum equals sum plus 2, and then etc. until sum equals sum plus n, and finally return. So these are runtime steps, and these are the description steps. Okay. So when we talk about complexity of an algorithm, we usually want the runtime steps. This is a common mistake students they usually confuse. I ask a question about what is the number of steps of this algorithm when n has some value, and the student just counts these steps here and says 3. No, that's wrong. This is just a description of the algorithm. But in terms of complexity, this is what matters. How many steps happen at runtime? Okay? So that's the difference between what is a step as a description and what is a step as an execution unit. So, okay, so I think enough blubbering. Now we need to get to the real thing. Now we start doing what asymptotic analysis. Okay, now asymptotic analysis is just a fancy word for saying we are going to see if an algorithm is efficient or not when n is very large. In order to know that, we need to find the growth function of an algorithm. So the asymptotic complexity of an algorithm, basically, in order to find the asymptotic complexity of an algorithm, we find its growth function. Okay, the growth function is the line which basically y equals x, number of steps in terms of input size. And we are going to divide the asymptotic complexity into classes. So some algorithms, they grow in a constant fashion. We have seen it. Some algorithms are linear. They grow like a straight line. Some algorithms are logarithmic. Basically, they start like this, and after that they kind of stay almost flat. Some of them are quadratic. Okay. Some of them are exponential. They grow really, really fast, etc. So these are classes. Now, in order to find if an algorithm is efficient or not, we are going to do the asymptotic analysis. Now, what does the asymptotic analysis mean? It means we are going to derive the growth function of this algorithm. And after we derive the growth function, we categorize it. Is it logarithmic like this? Is it logarithmic like this? Is it exponential like this? Or is it quadratic? Is it linear? Etc. And after this categorization, we can say whether an algorithm is efficient or not. We will see more about this later. Okay? And by asymptotic analysis also we want to do the, if you remember, we talked about absolute efficiency and relative efficiency. So sometimes we say an algorithm is efficient no matter what, and sometimes we say, well, these two algorithms solve the same problem, but the first one is better, is more efficient than the second one. Okay? So we have two things that we are for which we are going to use asymptotic analysis to decide whether an algorithm is efficient or not by its own, and to compare the efficiency of different algorithms that solve the same problem. Now, for the remaining several slides, for the next several slides, we will see some mathematical notation that is going to help us to decide if algorithms are efficient, more efficient than others, etc. Okay, so the first thing that we are going to see is something we call big O. So big O is just a big O. Okay, that's O, and that's big, so it's big O. Now, let's assume that we have two algorithms, A1 and A2, and they have growth functions Fn and Gn. Okay, so algorithm 1 and 2, for example, one has a growth function like that, another one has growth function like this. Okay, this is all that is saying. Okay, this is number of steps in terms of size of input. So algorithm 1 has got function that we call f of n, and algorithm 2 has got a growth function that we call g of n. Okay, now we say that of f grows no faster than g if the following predicate is true. Okay, this predicate, it's a first order logic predicate. If this is true, then f grows no faster than g. Now what does f grows no faster than g mean? It means the growth function of f, the growth function f, grows at a pace which is slower than g or equal to it. Okay, so what does this really mean here? Okay, so what does that mean? So we have, if we try to plot our number of steps by size of input, what we have in this case, for example, we can have a function that looks like that, and a function that looks like this. Now, which function grows faster? Is it f or is it g? Okay, so g grows faster because when, for example, when n is at this value here, f is still at this value while g is already at this value, and that's why g grows faster than f. So this is what this value, and that's why g grows faster than f. So this is what faster means. Okay, so f grows no faster. So if we say f grows no faster than g, that means f grows in a rate which is smaller than or equal. Okay, so no faster means less than or equal, right? So f grows no faster than g. Okay, no, before looking at this mathematical expression, if f grows no faster than g, then what can we say about the efficiency of algorithms A1 and A2?
Sorry again.
If A1 has got growth function fn and A2 has associated growth function g, then if we say that fn grows no faster than g, now what does this tell us about the efficiency of A1 and A2?
That means A2 grows up. Very one more going up. Very quick. Faster than A1.
Okay, so f1 grows no faster than g, so that means g is growing faster than f. Now if g grows faster than f, then which algorithm is more efficient, A1 or A2?
A1, A2. It assumes that A1 related to F and A2 related to G.
Yes, so in this case, which one is going to be more efficient?
A1.
Are you playing with a coin?
No. Coin. It's about. If F is lower than G, that means G is faster than F.
Right. Okay. Let's go back to our drawing. Now, if this is algorithm A1, and this we said algorithm A1 has growth function f, and algorithm A2 has growth function g. This is 2. Well, that's algorithm A2. Okay. So which one is more efficient here? Okay. So A2 is more efficient than A1, you say?
Yeah. No, A1.
I don't look very sincere, right? Okay. Here, so what is this saying again? This is saying that when n, for example, let's say when n is 1000, A1 takes I don't know, 500 steps, and A2 takes 2,000 steps. Now, which one is more efficient? Oh, okay. A1 is more efficient because it takes less number of steps. Oh, okay. A1 is more efficient because it takes less number of steps, a smaller number of steps than A2. Okay. Now, the function grows faster. If the growth function is fast, that means the efficiency is low. Okay? So, I mean, you have to be careful about that. If the growth function is fast, it means the algorithm is going to spend more time solving a problem, because even for an input which is here, for example, the algorithm is already here. It's fast. So, growth function fast means algorithm not efficient. So, in this setup here, when we say f grows no faster than g, that means that f is growing less than or equal, and hence algorithm A1 is better or more efficient than algorithm A2. So, let's go back to the mathematical equation. Are you familiar with these symbols?
Yes.
Existential and universal quantifiers, okay? So this is saying that there is a positive real number c, and there is a positive natural number n0, such that for all natural numbers which are greater than or equal to n0, f of n is going to be less than or equal c times g of n. Okay? Okay, so there is a positive real number, and there is a positive natural number, such that for all natural numbers which are greater than or equal to this number here, f of n is going to be less than or equal c multiplied by g of n, where c is this number here. Okay, so what this is saying is, in order to prove that function f is big O of function g, which means f grows no faster than g, if we want to prove that f is big O of g, we have to find a number c, and a number n0, such that this equation, this propositional logic here, proposition here is true. Okay, so we have to find n0 and c, anyone, okay, because it's existential quantifier. So c, n0, any values, we find them for which this expression here holds. Okay, if we do that, then we have proved that f of n equals big O of g of n, and consequently have proved that A1 is more efficient than A2. Okay, so these are just different readings. I'm not going to use them, but I mean, for your own knowledge, these are how you read the big O. Asymptotically dominated by G. G is an upper bound on F. So these are different readings how you read the big O. Now, here just another observation about notation. These are different readings how you read the big O. Now, here just another observation about notation. The equal sign here actually means a member of. When we say big O of Gn, big O of Gn is a set. It is not a function. Okay, so f of n is just one of these functions which are big O of Gn, g of n. Okay, so when we say f of n equals big O of g of n, actually what we are meaning is that f of n is just one function for which g of n is an upper bound. This is just a notation thing. In this course, in the exams, etc., we are going to use equal. But for your knowledge, equal here is not really equal that we are used to. It's actually a member of. It's just a notational thing. Okay. So in terms of geometry visualization, this is what we have. we have our function f of n and c times g of n, and we said for all n which are greater than some n0, remember input size in this case we are representing it by n, and this is the n0, after which f of n is always going to be less than or equal to c multiplied by g of n. This is the c which is a positive real number, and this is the n0 which is a positive natural number. So what we are saying basically, if it doesn't really matter if the functions intersect many times, we are going to look at the latest intersection, which we call n0. If for every natural number after n0 f of n is going to be less than or equal to c of g of n, c times g of n, then in this case f of n equals, or f is bigger of g. Okay, so this is just how do we visualize that expression. That's the n0, which is here, okay, and that's the c, and this is what it means by less than or equal, grows no faster. Okay, now let's see an example. Let's say you have this question. So we have algorithm A1, and algorithm A1 has got growth function f of n, which is this one, right? And algorithm A2 has got growth function, which is this one. Later on, we will see how to derive these growth functions, okay? But for the time being, assume you are given these growth functions, okay? Now, we have A1 with this growth function f, and A2 with growth function g, and you are asked to prove that f of n equals bigger of g of n. Which is just equivalent to saying 3n squared plus, okay, that's a typo. That should be 4n, not 4 to the power of n, okay. This is just saying 3n squared plus 4n plus 5 equals big of n squared. N squared is what?
G of n.
Yep, that's g of n. And this term, this polynomial here is f of n, okay? So f of n equals big of g of n.
G of n.
Yep, that's g of n. And this term, this polynomial here is f of n, okay? So f of n equals big of g of n. I have just substituted everything, okay? Now, this is just how we start doing the proof. So f of n equals big of g of n only if this term here is true. Okay, this predicate here, which is the one we've seen in the other slide. Okay, now we said that in order to prove this, we need to find a positive real number c, a positive natural number n, such that this relationship here holds. Okay, now here we are going to use a little bit of intuition. Okay, there is no one definite way that we are going to use in order to derive the values c and n0. Usually we will derive them by observation. Okay, you are computer scientists, and this course for you is some algorithm analysis course. You're not mathematicians. You're not required to do any rigorous proofs to find c and n0. You are just going to use a bit of intuition and common sense and observation in order to derive what is c and n0. And most of the time, it's very easy to derive them, at least for the examples that you're going to see in the lecture, or the examples that you're going to see in the exams, etc. So just by observation and intuition. Okay. So here, look at what I'm saying here. I'm saying that I'm taking this term, which is f of n, okay, and I am saying that this term is less than or equal to this term. Okay. What I'm saying is 3n squared is less than or equal 3n squared. Every number is, or every entity is less than or equal to itself. Okay, less than or equal is reflexive. Now 4n is less than or equal 4n squared, and that's true. That's always going to be true. And 5 is less than or equal to 5n squared. That's only true if n is not 0. Okay, so I'm saying by observation I can observe this kind of thing. And then I'm just summing up these. If I sum up these, obviously they are going to be less than or equal these here summed up. And this is what I'm saying here. Okay? That's what I'm saying in this part. I'm saying that the sum of these is less than or the sum of these is less than or equal to the sum of these. And then I can okay, now I am at this stage where I have shown that this is less than or equal to this. I can take n squared as a common factor here, and so I can add up all these terms together and I get 12 n squared. 5 and 4 and 3 gives me 12. Now I have reached a stage where I have an expression which looks like for all n greater than or equal to some natural number n0, and this is f of n, and the n square here is g of n, and I have found a c which is multiplied by n square by g